Let's get started. So index fragmentation is one of those really polarizing topics that seemed like something was really important a long time ago. There's a lot of built-in advice out there that says, oh, it's really important that you defragment regularly. And I even feel guilty because at one point in my career, I did a webcast called Fragmentation is the Silent Performance Killer. And it's one of those things I wish I could look back on and go, oh man, I wish I could erase that from the internet, because while it was true under certain situations, these days modern SQL servers are very different, and that advice really is no longer true. Things pivot over time, things that used to make sense, like the data versus log files thing we covered, putting them out onto separated drives. That used to make a whole lot of sense. Today it makes a whole lot less sense. We're going to cover what the whole fragmentation controversy is, and then once you decide to start rebuilding or reorging indexes differently, some pitfalls that you have to look out for along the way. Index fragmentation is super controversial. There's a big audience out there that says, oh my God, fragmentation is horrible. You have to make sure that you defragment regularly. It doesn't matter whether you're on solid state drives or not. Just fragmentation overall is bad. And then you got other people on the other side who are like, yeah, it doesn't really matter. It's not your largest problem. Go focus on the things that are your largest problem. The reason why we still care about fragmentation in this day and age is, say that you're out on vacation and you're enjoying the south of France, and then all of a sudden you get a text saying, hey, performance is bad, and the developers are all saying that it's because you don't have an index rebuild job. They refuse to do anything else until you fix this fragmentation problem. Then they might look on their code. I understand why people think fragmentation is a big deal, but to really think about why it matters and when it doesn't, we need to go spelunking into internals. And for those of you who have sat through my How to Think Like the Engine class, if you haven't, it's totally free. I highly recommend doing it. But if you sat through How to Think Like the Engine, you'll remember that everything in SQL Server is stored in 8K pages. That starts to change a little with things like column store is stored a little differently, and Hekaton, in-memory OLTP, is stored a little differently. But for most conventional, what we would call row store tables, everything is stored in 8K pages. And I kind of think of it as like the phone book. You think about the white pages of the phone book that Grandpa used to have above the fridge. The white pages of the phone book were organized by last name, then first name. Say that my phone book's completely full. Every page is absolutely full. On this page, I have Hall through logins. On this page, I have logins through Messina. On this page, I have Messina through Oates. And in comes Michael McDonald into our town. Michael McDonald moves in, and I need a place to put him, but all of my 8K pages are full. There's literally no space left on the 8K page that houses logins through Messina. What I have to do is I have to do a page split. I have to tear that page in half, so to speak, and put some of my residents on one 8K page and some of those residents on another 8K page. This is called a page split. And it got a lot of interesting reputations amongst early SQL Server tuners, because this means in order to write one row, I actually have to read the former page, write a new page that has some of my people in it, and write the old page. So effectively, adding one record has caused me to insert or write two different 8K pages to the database. Well, it gets a little bit worse, because every page in SQL Server is a doubly linked list. Every page has a link to the prior page and to the next page, so that if I need to scan through the phone book, I know which page to turn to. Now remember, when you and I think about a phone book, we assume all the pages are in order, but that's not the case here, because I didn't have any space left on the old page. It's not like I would duct tape a new page into the phone book. I actually add the new page wherever there happens to be free space in my database. So now on the page 4098, whose previous page used to point to 4097, I have to read him and write him too to change where his previous pointer goes to. And it gets even worse if you think about all the pages in the B tree that lead us directly to logins and Messina's page. I may have even had full pages at the tree level. I may have to split those too. There are two different issues here when we talk about fragmentation. One is out of order pages. When we added that new page with space for Michael McDonald, it was at the end of our phone book or somewhere in our phone book. I can't predict exactly where. This means that the pages on disk are not in order. If I go to scan my phone book, I'm going to be jumping around to move from one page to the next. Now, this only matters if you're reading data from disk. If you're reading data from RAM, what's RAM stand for again? Oh, it's not sequential access memory, it's random access memory. If you're accessing pages from RAM, it doesn't matter where they are in RAM. There's no sequential access to RAM anyway. So it only really matters if you go and hit the disk, which already you're facing a huge performance penalty for. No one ever said, I'll just go get this data from storage quickly. Data in RAM is fast, data from disk, not quite as much. There's a lot of controversy here around whether or not this actually makes a performance difference, and you'll see more details to back up later in the session why it really isn't that big of a deal. There is a separate part, though, which is empty space on pages. This is what we call internal fragmentation. Inside the page, I've got some pages that are half empty now, because when I had that completely full page and I split it in half, now I have two pages that have some of my data on them. There is empty space in each of these 8K pages. These 8K pages are the same in RAM and on disk. We're just shuffling them around back and forth. And this is the smallest unit of data that SQL Server will cache in a row store table, which means that if my pages are half empty, my RAM is half empty. Here's the really confusing part. Everyone agrees that this is bad for performance. Internal fragmentation is a bad deal because it makes your tables larger, makes your scans take longer, backups take longer, CheckDB takes longer. Your memory is effectively cut down in size because you're caching half-empty pages. But the screwy part is that a lot of us see fragmentation and go, I'm going to fix it by setting fill factor. But what does fill factor really do? Setting fill factor means I'm going to leave empty space on every one of these 8K pages. When you set fill factor, you are setting fragmentation. Say that you set fill factor at 80%. I want to leave 20% empty space on every page. You're saying, I would like my backups to take 20% longer. I'd like those index rebuilds 20% longer. Updating stats, could you make that 20% longer? My selects that do table scans, can you make those 20% longer? I'd also like to cut my memory in 20% by size. And you'll find out you're not fixing fragmentation, you're causing it. Even worse, database administrators often set it at the server level, thinking that on a transactional server, OLTP, where we do lots of inserts, updates, and deletes, I should leave empty space for page splits. But let's drill a little bit deeper into the contents of an 8K page. From How to Think Like the Engine, this is the clustered index of the users table. The users table at Stack Overflow is organized by ID. ID is an identity field, starts at 1 and goes up to however many. Now, all of our records are organized by ID. Do I need empty space on these pages? When I go to add new rows, I'm never adding new rows at a lower ID number. And I go to delete rows. I could be deleting rows from anywhere, but fill factor doesn't affect that. When I update rows, now this is a little different. When I update rows, if I had a field whose size was very small before, and I update him to be a value that's very large, I could conceivably cause a page split. Like, let's say that this row here, Arcturus, this guy who says he lives in NL, decides to change it to the Netherlands, and he needs more space. And let's say that all of this data was completely packed in. I might cause a page split there. But the odds are fairly low for most table designs. I only want to make this decision when I can prove that page splits are actually causing me a problem here. This is where measurements got really tricky because there's a perfmon counter for page splits. You may have seen it in the last session when I did SP Blitz first as a demo, and we looked down through the counters. I happened to call out page splits per second. The tricky part with that is that page splits also includes any time you add a new 8K page to the end of the row store. As I have more users sign up at Stack Overflow, they're always adding in new pages at the end of the table. The perfmon counter calls that a page split, and there's nothing wrong with that. It doesn't differentiate between a good page split and a bad page split. SQL Server simply calls any new allocated page a page split. And so by setting fill factor, you might look at this and say, well, I'm going to prevent page splits. But do you go back and measure to see that page splits actually go down? Or do you just pat yourself on the back for a job well done and miss the fact that page splits are still happening? It gets even stranger when you think about other kinds of indexes. Say we take the last access date index. In How to Think Like the Engine, we do a lot of query tuning around last access date. This index is on last access date and ID. So you'll notice that all of our users here are organized by last access date. Every time you log in or touch a page in Stack Overflow, that field is updated, showing that you last accessed the system on a certain date. Every time you log in, the SQL Server engine, goes in and picks up your record from wherever he is now and pulls him up and drops him at the end of the table because people always log in right now. No one logs in or accesses the system yesterday. It's always a current counter. Think for a second about what this page is going to look like after an hour or a day or a week. It's going to have empty spots all over it. It's going to look like Swiss cheese. It's going to have so many holes. And you might think that that's very fragmented. And that's true. It will show as fragmentation. But will fill factor fix that? By default, fill factor is at 100%. SQL Server crams the data in as hard as it possibly can. But when you set fill factor, you're saying, I'd like you to leave empty space on these pages. You don't ever need empty space on these pages unless Doc Brown goes and hops in his DeLorean and logs into Stack Overflow yesterday. Rows will never be inserted at a prior point in time. Again here, setting fill factor actually makes performance worse instead of better. This is where you have to peel things back a little deeper and understand what's really happening inside database internals and how we're making things worse when we go in and play around with knobs. My wife's worked for airlines for the longest time, and modern airplanes are really advanced. You can get an Embraer RJ, a small commuter jet. You can put in the exact airport you want to touch down at in the runway. The RJ will go all the way down to wheels down on the ground for you. You don't even have to lift a finger. Modern airplane pilots like to joke that there's really only two things in the cockpit these days. There's the pilot and there's a dog. It's the pilot's job to feed the dog. It's the dog's job to bite the pilot if he tries to touch anything. SQL Server needs a dog because we're in there, hey, let me stop with fill factor. Let me try to rebuild all these indexes. Let me play. Oh, that's going to make a big difference. And we don't know what we're doing. We're making things worse instead of better. First off, out of order pages are not really that big of a deal. When you go to hit storage, you're screwed to begin with. Empty space on the page, this is what's bad. And this is where setting fill factor makes things even worse. But there's this religious war over fill factor where people somehow think that reindexing or rebuilding indexes makes performance better. And usually when it does, it's because we blew away the plan cache. Rebuilding an index updates statistics on that object, which causes any query plans that touch that object to be flushed from cache. Then we get a brand new execution plan for the next set of parameters that come in. Suddenly that new plan is what people are excited about, and we get into this relationship where we're constantly rebuilding indexes. What Michael J. Swart likes to say is the world's most expensive way of updating your statistics and clearing your plan cache. There's nothing wrong with doing index maintenance, and I am a fan of doing index maintenance, but we're going to have to go a little next level deeper to understand what the differences are and when it makes a difference in terms of performances. For rebuilding an index, this means I'm going to go build a brand new copy of the index from scratch, perfectly packed in according to my fill factor, which in most cases really should be still at 100%. Cram that data into RAM as tightly as you can possibly get it. The bummer about about index rebuilds is that online index rebuilds are only available in Enterprise Edition, aka Expensive Edition. You may have noticed that Microsoft made a lot of things available in SQL Server 2016 Service Pack 1. All of a sudden, a bunch of enterprise features were dropped down into standard. Online index rebuilds was not one of those things. Honestly, all the DBA features are still up in enterprise. It's just the developer ones that got dropped down to standard. Reorganizing our index just means basically shuffling these 8K pages around so that they're physically in order. But that's where you're still kind of screwed, because that didn't really matter. All you're doing is generating a lot of transaction log activity, and it's single-threaded. It takes forever for this thing to do its job. Microsoft recommended that 5% once your indexes hit 5% fragmentation, you should start shuffling pages around. And when you hit 30% fragmentation, you should throw that object away and build a brand new one from scratch. The problem with that is it generates a ton of transaction log activity, and it blows away your plan cache for any object that you're rebuilding. I'm like, you should probably ease off on that. I'm fine with rebuilding indexes when they hit, say, 70% fragmentation, but lower than that, let's not write so much to our transaction log. Let's not make database mirroring and always availability groups and log shipping get so far behind. Instead, let's just ease up and only do a reorg if we hit 30% and only do a rebuild if we hit 70%. Now, if I have Enterprise Edition, Fred says, yeah, that's cool. Fred, we'll talk about that in a while. So there are downsides to using online index rebuilds too. So you'll see a lot of us who have Enterprise Edition will try to use online index rebuilds. It's probably one of the most popular things out of Enterprise Edition there. We say that it's mostly online. At the end of its rebuild operation, it does need a momentary schema mod lock in order to switch in the brand new copy of the index. So starting with SQL Server 2014, I can say, I want to wait at low priority. Other people can jump in front of me, and this can avoid the problems with big, long blocking chains that I can see even during an online index rebuild. Here's how the command works. I can say alter index on this table rebuild with wait at low priority, max duration 1 minute, and if after 1 minute I'm still waiting for a lock, just kill myself. You can also kill blockers, which can make sense in a data warehouse environment if there's just a bunch of selects that are going through and you don't mind making them fail in order to get your big, huge, ginormous index rebuild finally in through the door. The reason why this prevents blocking chains is up at the top, I have a regular index rebuild command running. Down at the bottom, I have the fancy new one with wait at low priority. Let me explain what's going on here. At the top one, I started my alter index and he made progress for a while. Somebody else snuck in and did a begin tran. They're deleting a few rows from the same table I'm rebuilding. Now I'm waiting on a lock for that delete to finish. I am doing an online index rebuild here, but it doesn't matter. Even though it's online, I need to change the schema of this table. That means anybody else who's doing a select even with it no lock. This particular select is running with no lock, but he still gets blocked by my alter command. Reason why is a select, even with a no lock, needs something called a schema stability lock. It needs the schema to remain in the same shape as when it started. I can't have a table suddenly have more columns halfway through my query. SQL Server isn't smart enough to recognize that an alter index rebuild isn't really modifying the table, so that select, even with no lock, has been blocked by my query for over a couple of minutes now. If I jump down though, down in the bottom one, I have my alter index rebuild online happening, but I've said instead of waiting for a schema mod lock, I'm waiting at low priority. And you don't even see the select happen with no lock here. It blazes right on past because my alter index rebuild is just kind of waiting out in the background going, whenever you're ready, I'll make my change, but the rest of you go on ahead. I still am waiting for that begin tran to finish, but at least I'm able to wait at low priority. So that change in SQL Server 2014 was the first big fix for online index rebuilds. That doesn't fix the second problem with them. Performance. Performance for online index rebuilds is actually worse, much worse, than offline index rebuilds. In order to show it, I'm going to show 5 different tests. The top 2 tests are rebuilding with 4 cores. I'm saying go take the index online while it's up and running, rebuild with MAXDOP 4, so use up to 4 threads. This one does it offline with 4 threads. The next pair do MAXDOP 1. And if you have MAXDOP set at the server level, that also takes effect on the maintenance jobs as well. Check DB, online index rebuilds. So online indexes with a rebuild of MAXDOP of 1 is a lot like having a SharePoint server where MAXDOP is set to 1 and it isn't changed for the agent jobs and nobody hinted the query. Alter index rebuild with online equals on, MAXDOP equals 1, or offline. This is the equivalent of standard edition. And then finally, I'm going to show you one other test, which is reorg. Just single-threaded, move my pages around. This is always single-threaded, but it's online in both standard and enterprise. Deep breath. Here's the test results. So looking at these, I've got columns for duration, how long it took, CPU, the number of page reads that we did from disk, the number of logical reads that we did from RAM, and then writes. Let me rephrase that. Logical reads, it's reads regardless of where they came from. They could have been in memory or had to hit disk. And then the number of writes that we did. Now, it's probably not a surprise that single-threaded index rebuilds are much slower than everything else. But what's interesting is that doing it online, single-threaded, is way slow, twice as slow as taking it offline. Yes, it does let it happen without any queries getting blocked by anybody, as long as we're on 2014 and we do our wait at low priority trick. But this is way slower than the rest of the options. If you're on Enterprise Edition, say that you're on Fancy Pants Enterprise Edition, and you can do these index rebuilds online, you want to throw lots of cores on there. If your server is throttled at MAXDOP 1, it's time to think about hinting your individual index rebuilds to make them go much higher. Ola Hallengren's lets you set MAXDOP and passes that through to every index rebuild command. The fastest one, something like 7 times faster, is doing it by taking the index offline and throwing multiple cores at it. So this can start to make sense with data warehouses, where at the end of our nightly jobs, or maybe at big seasonal maintenance windows, I'm going to say, all right, everybody out of the pool, I'm going to rebuild these indexes and get it done as quickly as possible. Reorganize, still faster than single-threaded index rebuilds, but it does do a ton of reads because it's literally picking up pages one at a time and moving them around from one place to another. Summing it up, online indexing rebuilds, it's an Enterprise Edition only feature, but it does have drawbacks. It's slower, and you can only offset it really by throwing lots of cores at it. In order to not take objects offline, you want to use the new wait at low priority feature. And of course, use Ola Hallengren's maintenance scripts to allow this. He has parameters just for this too. It gets worse. There was a bug in SQL Server 2012 and 2014 where parallel online index rebuilds could corrupt data. If for some reason during your parallel online index rebuild, SQL Server had to roll it back for some reason, it would leave some pages as corrupt. The fixes for this, well, you either do your index rebuilds offline or you do them single-threaded, just one MAXDOP of 1. It's another great reason why you keep up to date on patches, and we'll talk about patching in the next module too. So should you set fill factor? Should you play around with that? The next gotcha around index rebuilds is to look at the differences between these two tables. If I just go with fragmentation as my measure, I have one table that's been heavily inserted, and as a result, it's fragmented really bad. I have another table that I just, exact same number of rows, I rebuilt it right after this test finished, and I rebuilt it with 75% fill factor. So this way, all of the pages are perfectly in order. All my ducks are in a row, but my pages have empty space on them because I want to prevent fragmentation from being a problem for me in the future. Which one of them is better? Shockingly, it turns out that the table with 51% fragmented is actually better. There's more rows per page and there's less pages in the index. Granted, it's scattered all over the place instead of being nicely in a row, but when I end up querying that thing, as long as I'm querying it from RAM, there's not going to be any kind of difference to that thing whatsoever. The one that is able to cram more pages, more rows per page, is going to end up performing better. When you set fill factor, SQL Server remembers the fill factor going forward. This is where SP Blitz Index is super useful to go analyze the indexes across the database server and say which ones were purposely rebuilt with, say, a 50% fill factor. I wish this wasn't true, but at least once a quarter, we see someone with a 10% or 20% fill factor. True story, in the last 30 days, we've seen 2 shops with a 1% fill factor. Simply by rebuilding their indexes with a 100% fill factor, the data started fitting in RAM, their backups were going 10, 20x faster, and it wasn't a matter of setting fill factor at the server level, just someone had gotten a little fancy pants with index rebuilds at the table level, and then they were stuck. Next option that you get when you're doing index rebuilds is there's a thing called sort in tempdb. Sort in tempdb lets SQL Server go build the new copy of the index over in tempdb and then push the final copy up into the user database instead. This can make a difference if you're on a failover cluster or anything with local solid-state storage and then slower shared storage. A great example of this these days in the cloud is SQL servers and VMs that have local ephemeral storage, throwaway solid-state storage that's way quicker than their provisioned shared storage. It makes a tremendous difference based on your SQL Server version and a version 2 as well. There was a patch in 2012 and 2014 where SQL Server tries to hold more data for tempdb in RAM instead of flushing it out to disk. This pays off on online index rebuilds as well. Yet another reason to keep your SQL Server 2012s patched. The next thing that catches people is advanced readahead. So in theory, remember in the storage module we talked about merry-go-round scans? Well, there's another feature in Enterprise Edition where when SQL Server, the engine, sees you reading a large amount of data in a row, if that data is beautifully defragmented, SQL Server says, well, I'll issue larger read requests because I bet normally if, say, I only issue a 64K or a 128K read, odds are those coming extents are all the same table. But if I know this thing is really defragmented, I'll go ask for, say, 512K at a time, gambling that the next several extents all contain data for my one table. Well, there's a catch. What if I rebuild my indexes multi-threaded? What if I use, say, MAXDOP 4 on my index rebuilds? My index is not laid out cleanly in a row at that point. It's actually fragmented on disk. I'm building several different parts of my index on different places in storage. So, in theory, SQL Server will recognize this as fragmentation and do smaller readaheads. Thereby, some folks will say you should rebuild your indexes with a MAXDOP of 1 to make sure all your ducks are in a beautiful little row and you get larger readaheads. This experiment is going to be a little bit more complex, and I'm going to have to show you something that I haven't used in the rest of the training, SPBlitz trace. SPBlitz trace is a stored procedure Kendra Little wrote to go set up an extended event session and trace everything that happens in that session. The only reason I'm showing you this here at this point is that I need to prove just because you ran an alter index with a MAXDOP of 4 doesn't mean it actually went parallel across 4 threads. MAXDOP isn't the same as a MINDOP command. MAXDOP just says, SQL Server, you're allowed to use up to 4 threads if you want to, but you don't have to. There's no such thing as a MINDOP command, although there's a very popular connect request to get us one of those. So I'm going to fire up SPBlitz trace, which will capture degrees of parallelism among lots of other things it'll capture. Start it up, rebuild my index with MAXDOP 4, stop my trace, and then read that trace. I'm not going to teach you guys how to use SPBlitz trace in here, although if you like what I'm doing, you may like what we're doing in a few more slides about SPBlitz trace. Feel free to go grab it. It hasn't been updated in probably 3 years because it just does what it needs to do, and we're done. Notice in here it says, all right, my batch completed, alter index, and the degree of parallelism was 4. Now I'm going to use SPBlitz trace for something else. SPBlitz trace will capture lots of things, not only just degrees of parallelism, but it'll also capture how many reads you do. Now, I'm going to do something a little weird here. I'm going to bucketize my reads. I'm going to say that I want to count how big of requests I do, how many 64K requests I do, how many 128K, how many 512K. Because the theory is, if I do larger read requests, that's a good thing. And sure enough, the extended events trace actually bears that out. On the left-hand side, if I do a select on this table after I rebuilt it with MAXDOP 4, here's the size of my I/O, and here's how many of those I/Os I did. You'll see that I did about 6,000 requests at 256K per request. Whereas if I rebuilt this index with MAXDOP 1, meaning all of the data is laid out in a perfect little line, I did half as many I/O requests and they were twice as large. So the moral of the story is you should rebuild all your indexes with MAXDOP 1, right? So that you get these big advanced readaheads. Not so fast. Let's dig a little deeper. Just because the queries did large readaheads, were they faster? And in this case, at the top, after I rebuilt the index with MAXDOP 1, the query took about 10.5 seconds in order to run. After I rebuilt the index with MAXDOP 4, this is the more fragmented index, my queries took about 10.5 seconds to run. Is there a tiny difference between the two? Of course, but it's just a tiny difference. Can you really afford to have your index rebuilds take the entire night in order to shave 1 or 2% off the speed of your queries? It does produce larger reads and better read ahead, but who cares? Our queries weren't significantly faster. This is really the whole big argument around fragmentation. People often think that they're going to have these perfectly aligned pages in disk all in a row, but when you measure performance, you look at the bottom lines on all these tests, and end users don't notice a difference. They do notice a difference with half-empty pages, but not getting those pages perfectly in order on disk. So let's figure out how we're going to do it. The way that we're going to run our index maintenance commands, here's Ola Hallengren's maintenance scripts. Now here's what we recommend setting for index maintenance. Once you understand the mechanics behind this, Ola Hallengren has this really simple stored procedure. Minion, the MidnightDBA folks have Minion reindex as well. That's completely fine. It's table driven. Nothing wrong with that. I usually prefer Ola's because it works really well and I'm used to it. I've been doing the same thing for years. With Ola's, he has, if your fragmentation reaches this percentage, say 30, then go do this, index reorg. If it reaches 70, go do this. First, try to do a rebuild online if you can. If not, do a reorganize. If you've used Ola Hallengren scripts before, you may notice that the stuff I'm recommending here is different than the way Ola starts out by default. I am defaulting to less aggressive index rebuilds. He follows Microsoft's 5 and 30%. And I'm also giving my index rebuilds less options. Ola, by default, will try to do a reorg. If he can't, he'll try to do a rebuild online. If he can't, he will do a rebuild offline. I'm not a fan of taking objects offline if I'm not around to see it. If you have the kind of system where it doesn't matter if you take objects offline, then good for you. But if you do have a 24/7 type shop, I would ease up on the offline index rebuilds just because I don't want that call from my end users. Going further in Ola's parameters, he has all kinds of different options. Should you update your statistics? What's the longest that you should run for? How much should you delay between indexes? This gives your I/O subsystem and your database mirroring and always-on availability groups a chance to keep up before we overwhelm the storage subsystem. What your MAXDOP should be, all kinds of really cool parameters. I'm not going to go into all of those details here, but you get an idea of just how powerful this thing is. And before you get too comfortable, index rebuilds have a few gotchas. First off, there's a bug in Fred says, can you use MAXDOP with 2012 Enterprise on index rebuilds? Off the top of my head, I'm fairly sure you can. I think MAXDOP has been a command for index rebuilds, I want to say since 2012, but check for books online. One of the awesome things about Ola's is he detects what version and edition you're on, even down to service packs, and the schemas of your tables to figure out what parameters he can pass in and what you can't. So you can always try MAXDOP 4 and then see what comes out of the output, whether it actually goes multi-threaded. In unpatched versions of SQL Server 2012 and 2014, when you rebuild an index, it clears usage statistics. This is kind of painful if you like using SP Blitz index to track which indexes are heavily used and which indexes are not used. There was such a chorus of us, chiming in on the Connect item when it first came out. Please don't ever do this again. We need our index usage statistics. Next gotcha in there is that remember, whenever you're doing index rebuilds or reorgs, these are logged operations that will push a ton of data downstream, whether I'm talking about transaction log shipping, mirroring, or always-on availability groups. It also shuffles pages like mad. So if you're doing SAN snapshots, or VMware snapshots, anything that takes pictures of your storage and then tracks what changes, you're purposely inflating the sizes of your backups. So make sure you're fixing something that's actually a problem. Next big known bug was always-on availability groups. When you would rebuild an index, if you had multiple replicas, you would burn up your RAM with multiple copies of the transaction log, one per each replica. Just another reason why you got to be careful with always-on availability groups. We finish this up with a series of best practices and a set of decision trees. Generally, we are a fan of only reindexing when you seriously have a performance problem or when you have a whole lot of empty pages inside an object. If you're under a time crunch and you want to crunch this thing down to a smaller maintenance window, make sure you're going parallel. If you really need to, you can take objects offline. Classic examples, data warehouses, where I have a very limited amount of time overnight, and I can guarantee that no one's making queries at the same time I need to do my index rebuilds. Then I can take those things offline. We've got a series of decision trees here that I'll let you read on your own. The big takeaway with this is just that if end users aren't complaining, leave your index maintenance plans the way they are. Unless you're rebuilding everything every night. If you're using either maintenance plans or even Ola Hallengren scripts that start out with that aggressive 30%, it's time to back off on those thresholds. Give you a few other decision trees here. And then finally, just as a last ditch, if you don't need online, try rebuilding offline, and then make sure you're scheduling so that you're not doing everything exactly the same time. Doing backups, check DB, index maintenance, and parallel statistics jobs all at the exact same time. Martha says, can you talk about the index and SAN stuff you talked about yesterday again? Yeah, so with SAN snapshots, the SAN is taking a picture of where all your data lives, and then whenever your data changes, it's going to write that data to a new location. So you need additional space for your snapshots based on your database's change rate. Well, when you rebuild an index, you're not really changing data. All you're doing is moving it around. And yet the SAN has to keep all those new pages that you're generating. So we're artificially inflating the sizes of our snapshot backups without getting any kind of payoff. Also, if you're doing automated tiering, where the SAN knows to put the frequently accessed blocks on faster storage and the less accessed blocks on slower storage, if you have tables that frequently fragment due to heavy inserts, updates, or deletes, then constantly rebuilding those guys means you're pushing them up into the fastest storage that you have, when ironically, these may be the tables that you care about the least. I've seen a lot of shops where they have, for example, a logging table with a GUID as a clustering key, and they're just dumping data into that table and nobody really cares about it. And yet because it's fragmenting like crazy and we're rebuilding it like crazy, it ends up being the one hog of all our really nice solid state storage while everybody else is down on slow rusting spinning disks.